So again, we're going to look at something we've seen before. The only difference, using radians instead of degrees. So graphing our basic trig functions. So let's start with the sine curve, and we know the amplitude's 1, so we go up to 1, down to -1, and I usually mark off the boundary values, but now it's in radians. So instead of labelling 180 degrees, I label pi and 2 pi and so on in each direction. The sine graph starts at the origin, and then we know it goes up to the amplitude, then back down to the axis, and then that pattern repeats up and down, up and down. We draw a nice smooth curve through it all. There's our sine curve. And we know things like the domain, there's no breaks in it, it's all real x. The range, going from -1 to 1, it's an odd function. We've got rotational symmetry. So that means when we're playing with it, we know the sine of minus x will be the same as minus the sine of x. Period. The period is how long it takes until it repeats, but repeats in exactly the same position and travelling in exactly the same direction. That's why it's better to look at the amplitude rather than the x-intercepts, because you start at 0. The next x-intercept's at pi, so you might think, oh, we're back there at pi, but it's going in a different direction. See, at 0 the curve's going up, but at pi the curve's going down. It's not until we get to 2 pi it's going back up again. So probably the amplitude is a better spot to pick to look at and see what the period is. And so the period is 2 pi radians. Amplitude, how far up or how far down it goes from the axis, and that is 1. Okay, cosine curve. So again, let's mark off 1 and -1 and our divisions. So every pi on 2. But what we know about the cosine curve is it starts at the amplitude. So that's the first point I'll mark in. Then we go down to the axis, and then we keep going down and then up and down, up and down. Our little zigzag pattern, but again, we don't draw a zigzag, we draw a nice smooth curve. Basically, it is the same graph. Domain is all real x then, same domain. Range, -1 to 1, same range. But this one's not an odd function. We've got symmetry in the y-axis, so we have an even function, which means cosine negative x will be the same as the cosine of x. Same curve, so same period, 2 pi, amplitude is the same as well. Basically, we've got some shift happening. If you recall from when we were shifting graphs, you could think of the cosine graph as the sine of pi on 2 minus x, because what we've done is we've reflected the sine graph in the y-axis and then shifted it to the right pi on 2 units. And what's significant about the pi on 2? Well, pi on 2 or 90 degrees, that's where the co comes from. The prefix co stands for complementary, and complementary angles add up to 90 degrees, or pi on 2 radians. Alright, let's look at the tangent curve then. We don't worry about an amplitude with the tan graph, because if you recall it goes up to infinity down to minus infinity, but we will mark off our divisions. We start at the origin with this one, but then we get a vertical asymptote at the next boundary, and that pattern is repeated. So we have x-intercept, then asymptote, x-intercept, asymptote, and so on. We have to bend towards the asymptotes. We also know the tan curve is positive in the first quadrant, so between 0 and pi on 2, so I know I'm up there. But in the fourth quadrant, it's negative, so I know I'm down here. And then that repeats between all of our asymptotes. There's the tan graph. The domain, a little bit harder to write because of all those asymptotes. So I just picked one of the asymptotes. Seems logical to pick the first one. So pi on 2. And then what I'm saying is, well, every multiple of pi before and after it. So pi k, where k is some whole number, some integer. The range is everything. There are no breaks, so it's all real y. And this is also an odd function. It has the rotational symmetry. So we know the tan of negative x is the negative tan of x. This one repeats every pi. So the period is pi for the tan curve. And we don't talk about amplitude because it just keeps going up and keeps going down. So you don't really have an amplitude of a tan curve. All right. Let's do one of the reciprocal curves. So let's look at the cosecant. So to begin with, I'll draw the sine curve in because cosecant is the reciprocal of sine. But I'll just dot it in. There's our basic curve. it's not part of our new curve we're going to draw, so that's why I've dotted it in to say, no, this is not part of the curve, I'm just using this to help me out. Now what do we do with reciprocal graphs? We know the x-intercepts become asymptotes, because you can't have 0 on the bottom of the fraction. So at every x-intercept we have a vertical asymptote there. 1, well, when you turn 1 upside down you get 1. So every point on the original curve where the y value is 1, or -1 for that matter, it will still be at that point. The y value is not going to change. But of course any number that's smaller than 1, when you turn it upside down, will become bigger than 1. Now our curve, our basic one there, sine x, is always between -1 and 1. So when we turn it upside down, it should always go outside of those. And we've got to bend towards the asymptotes. We end up with these U shapes. They're not parabolas, they're just U shapes. So y equals cosecant of x. So 11J is just looking at drawing our different trig functions.